Good evening, everyone. Welcome again to the Special Functions and Number Theory seminar. Our speaker from today is Professor Aninda Sinha from Indian Institute of Science, as well as University of Calgary. He'll be talking about field theory expansions of string theory amplitudes, and in particular on some cool formulas for pi. So, over to you.
Okay, thank you very much for the invitation. It's a pleasure to give this seminar. I love to interact with mathematicians, although not as much as I would like. Hopefully, this is going to be a platform to change that. So I'm going to talk about this paper that came out earlier this year called Field Theory Expansions of String Theory Amplitudes. So this is actually not a one-off. This is an area of research that we have been working on for the last several years. Although my main focus is going to be this paper written with Arnab earlier this year. But this actually made use of technology that we have been trying to develop over the last several years, in particular with my student Ahmadullah Zahid and also a postdoc Prashant Raman. In fact, since the audience is mathematicians, this third paper may be of some interest because this connects up with geometric function theory, for instance, the Bieber-Bach conjecture and Rogozhinsky bounds and things like that. And this line of research originated from exploring a particular area of physics called critical phenomena. Roughly speaking, what we were trying to do was to try and set up calculations without encountering the standard UV divergences that one sees. So whenever you try to do some calculation using Feynman diagrams, you see infinities. And so the program was to try and see if we could write down a set of equations where we would be able to extract physical quantities without encountering infinities. And this was done over the last several years in collaboration with Rajesh Gopakumar, Apratim Kaviraj, Kollol, and also a follow-up paper with Rajesh and Ahmadullah. So without further ado, I think many of you know that our paper was not really about pi, although pi got the center stage. The formula for pi was in fact in the last paragraph of what is the new end matter of this physical review letters. So they have introduced a new format where you can add an appendix. So previously you wanted to squeeze everything within 5 pages or 6 pages, including references, but now they are more generous. And in fact, the last paragraph says that if you put particular values for this two-variable function that I'm going to talk about a bit more, the Euler beta function, a slight generalization of the Euler beta function which arises in string theory, you get a formula for pi. If you look at the summoned in the parameter going to infinity limit, this becomes the Madhava series. And also, I should point out that when we claim fast convergence, this is with respect to the Madhava series, and certainly we did not say that the series is going to converge fast compared to some representation that Ramanujan, for instance, had found. And so the center stage was this new formula for pi, so let me just flash that. So this looks very similar to the formula that you see in Madhava series. So Madhava series, the formula starts with 4. And so in order for this to converge to pi, you require large corrections. And the formula that we came up with had a parameter lambda. So it's an infinite series as well. So this is the rising factorial. This object here is the rising factorial. This formula came from QFT considerations. So what are the new elements in this formula? So there is a parameter, and the parameter can be real or complex. It doesn't matter so long as the real part of lambda is bigger than -1. It's a free parameter, and for any value of this parameter, you're supposed to get pi. And just so that we are notationally on the same page, this symbol here means the rising factorial defined like so when n is an integer, and through ratios of gamma functions when n is not an integer, but then whatever I'm talking about, n is always going to be an integer. And if the argument here is 1, it becomes the ordinary factorial. And there are some curious features about this formula, so let me just point them out. This might be of some interest to members in the audience. If lambda is very big, then the summon behaves like the Madhava series, but the Madhava series, as you all know, has this alternating sign, so it's a conditionally convergent series, whereas this is actually absolutely convergent. So the tails of the series are going to be different. And another something very interesting happens if lambda lies between minus quarter and 1, then each term in the summand is negative, unlike Madhava series where you have alternating signs. So there are some interesting quote unquote positivity properties. I'm quoting quote unquote because actually the operative word here is negativity, unlike Madhava series. And of course, a bizarre fact and something that is fun to play with is that you can put lambda to be any multiple of pi and the formula should still work. And if you truncate, you get an approximate polynomial equation for pi. And I should point out that this formula and the proofs and extensions were proven using continuous fractions by Halmar, and you're going to hear from him next week. So because we are physicists, once we have a formula, we want to play with it. So we go to Mathematica and then you just play with it and see whether you can get pi to as many decimal places as you want. So this is a sample game that we play. Now that you have Mathematica, you can do whatever you want. So here is a demonstration that the formula agrees up to 500 decimal places. I chose some random value of lambda here. And so you can play all kinds of games of this kind. And I should point out that we took inspiration from Newton, who also played with, of course, on pen and paper and hand. He himself used the inverse sine to compute a 15-digit approximation to pi in 1665 or 1666. And writing, I'm ashamed to tell you how many figures I carried these computations, having no other business at that time. So I also did not have any other business, and I just asked Mathematica to verify these formulas. And the picture that emerges, you can diagrammatically indicate it in this manner, so on the x-axis we have the number of terms, and on the y-axis we have this parameter lambda. So when lambda is small, so specifically when lambda is minus a half, you get something that I would like to identify as the formula that would arise from string worldsheet calculations. So don't worry about these terminologies. Whatever terminology is unfamiliar, I'll try to explain it later on. And as you dial lambda, there is some optimum choice of lambda which gives you the minimum number of terms. So this is something that I don't have a quantified estimate. I just have some numerical estimates that the picture must look like this. And when lambda is sort of in the middle range, then I would like to identify the physics interpretation of the formula as arising from Feynman diagrams. I will distinguish what I mean by Feynman diagrams and what I mean by string later on in the talk, so that all of us are on the same page. And as lambda becomes bigger, it becomes close to the Madhava series. So in some fancy physics terminology, it is as if there is an extra dimension that is there, and it is trying to find the geodesic or the shortest route by exploring this extra dimension. And so that is why I call it holographic pi. So this is just a cartoonistic impression as to what might be a picture to have in mind. And I should also point out that because this is a number theory and special function seminar series, you might be interested to know that, I guess this is very well known amongst this audience, that there is in fact a geometric or number theory interpretation of the Madhava series. And this is something that I learned relatively recently. So the argument was due to Gauss and Jacobi, and can be found in this classic textbook by Hilbert and von Vossen. And pi here is related to geometry and counting. So in particular, you need a formula to count the number of pairs of integers such that x square plus y square is less than equal to n. And by solving this counting problem, you can massage the representation for pi to be the same as the Madhava series, or the Madhava-Leibniz series as it is referred to. And this is an open question, and this is something that I would like to know the answer, and this is something that I don't know the answer, is there a similar counting that gives this parametric pi? One suggestion that I have is that instead of actually looking at this uniform square lattice, it will be more interesting to look at hyperbolic lattices. And the reason for that is that if you consider hyperbolic lattices, then most of the area is going to come from the first, this pentagonal structure inside. And so it would actually, at least it seems naively to me, that if you consider this hyperbolic lattices, and if you were able to do this counting problem using the hyperbolic lattice, then convergence would be faster. So this is just a suggestion. I have no other proof that this is how you can argue for this parameter lambda in the series, but this should be fun to figure it out. So since we are physicists, once we have a formula that we derived, and now I'm going to say that, of course, we have a derivation, but at the same time, there is a sort of a distinction between the way that mathematicians work and physicists work. So this cartoon here actually says what the distinction is. So here is a professor talking to a student, and in mathematics, you come up with a proof, and the professor says, this isn't a proof. You can't have a whole step that says Mathematica said so. Whereas in physics, here is another professor talking to a student. What a waste. Half of this proof could be replaced by Mathematica said so. And so I think one has to, I don't want to be flippant here, but I would like to point out that I think there is merit to both points of view. And of course, you're going to hear my point of view in this talk and Halmar's point of view, and how Halmar's point of view actually can be useful for us as well is what I'm going to indicate towards the end of the talk. So here is the outline of my talk. I'm going to first tell you what we were trying to do and what the physics reasonings behind trying to look for these parametric representations were. And then I'm going to talk about the Euler beta function in string theory, a puzzle, associated puzzle, and what the resolution is. Then I'm going to sketch the dispersive representation derivation using dispersion relations. So what are these fancy dispersion relations that we're going to use, because they are novel, they did not exist before our work, and some new technology was developed, at least from the physics perspective, over the last couple of years. And then I'm going to tell you how this shift symmetry, which introduces this parameter lambda, how it came about. And finally, I'm going to talk about where next, where I'm going to talk about closed strings and how to use what is called the bootstrap technique to find generalizations of these kind of string amplitudes. And the main goal of my talk here is to find a common language. And so please don't hesitate to ask for clarifications, because sometimes I might be using jargon which physicists may be familiar with, but mathematicians may not be. So if I'm using some jargon and you want clarifications, please, stop me and I will try to explain. So are there any questions so far? Can I go on to the next one? Okay.
Sure.
Yeah. So what is it that we were trying to do? Now, contrary to what you may think, it was not a paean to string theory. Paean is a fancy word for singing praises of string theory. Rather, it was trying to address a pain that exists in the minds of many practitioners of string theory. Yes. There's some disturbance. Any questions? No. And unmuted. Yeah. So I will explain to you what this pain is. And for this, I require to explain a little bit of quantum field theory. So let me, the title of my talk also, the title of my paper also, our paper has field theory expansion. So I need to explain to you what field theory is. And it's don't be scared, because the amount of field theory we are going to require is going to be very little. So here is a 5-minute crash course in quantum field theory. The aim for the next bit of my talk is so that we use the same terminology, so that you don't feel alienated with some of the words that were used in our paper. So QFT is a short form for quantum field theory. So QFT also stands for another famous thing called quantum Fourier transform. That is not what I'm going to talk about. It's quantum field theory. So what is quantum field theory? So hopefully all of us are familiar with Maxwell's equations for electromagnetism, which I guess nowadays we learn probably in high school or maybe the first year undergraduate course. So we talk about the electromagnetic field. So a field is some function, and the function is, so it's a function of the space-time coordinate. So it's a function of time as well as the three space coordinates that we have. So if you are in 1 plus 3 dimensions, but we can pretend to be in any dimensions that we want. So you can generalize this concept to any dimensions. And in modern parlance, the notion of field is important because we want to be consistent with Einstein's special relativity. And it is difficult to have a consistent theory which is consistent with special relativity otherwise. So what is quantum about it? The fluctuations of these fields, electromagnetic field is one of them, gravitational field is another example of the field. So fluctuations of these fields are identified as particles. So the fluctuation of the electric field would be identified as the photon. So something that, a concept that everybody is familiar with. A bit more mathematically precise way is to say that these particles are labeled by two quantities. One of them is the momenta, so how fast the particle is moving. So there is a relativistic notion of that quantity, which is called the relativistic 4 momenta, 4 because we are in 3 plus 1 dimensions. And another quantity which is called spin. So just, you don't have to worry about what these are, just know that there are two labels. And what we do in quantum field theory is we typically start by specifying the kind of particles that are there in our theory. And we typically start by specifying particles in a theory where the particles are not interacting. So they're just moving freely without talking to each other. So for example, let's consider a spin 0 or scalar particle. So everybody has heard of the Higgs boson, for example. So Higgs boson is an example of a scalar particle. So you could consider a setup where you have mass of various kinds. So let's consider mass increasing in the positive y direction. So let's label the fields which are light or which are very sort of close to being massless as phi 1 and phi 2. And these are what we will call as light particles. So light is not the same thing as light in the tube light or something. This is light in the sense of the mass of the particle. And then let's have in our spectrum some heavy particles which are labeled by psi 1 and psi 2. So in physics parlance, when we talk about low energies or low mass, we use the terminology infrared sometimes. And when we use high energies or high mass, we use the terminologies ultraviolet sometimes. And the nomenclature comes because in the spectrum of light, Vibgyor, when you go towards the red part of the spectrum, the energy contained by a photon of that wavelength is smaller than the energy carried by a photon which has wavelength closer to the ultraviolet. So if our energies are low, you would have thought that maybe we don't really require to keep in our description of the low energy physics these high energy particles because we are not going to excite them. And this is the intuition that we have as physicists, that maybe we can just go forget about these very massive particles and we can just focus on these light particles. And this approximation goes by the name of effective field theory. So if you hear the words effective field theory in any physics talk, this is what, roughly speaking, you should have in your mind. So what do we do next? We then specify interactions. So for example, light that is coming out of the tube light interacts with the electrons that are moving in the wire, for example. And we need to specify how the electron and photon interact. And what I mean by interaction is with what strength they talk to each other. So after we specify that, what we calculate in quantum field theory is the probability of particles scattering off each other. So an electron can go and interact with a photon and scatter off each other. And our detectors actually measure these particles which are scattered off. And that is how we learn about what the microscopic description of this physical phenomena is. And sometimes, you will hear me use the word S matrix. So we call the unitary operator, so unitary in the sense of a unitary matrix, such that S dagger is equal to 1. We call the unitary operator that takes the incoming particles to outgoing particles as the S matrix. So what we think of is that we prepare these particles and they're not interacting. They come and collide and they go off again in future time and a lot of time later, we collect these particles in our detectors and we try to understand what was going on at the level of interactions. So typically, we calculate using the machinery of Feynman diagrams. So let's suppose we have, in this toy example, a blue particle and a red particle, and they are interacting via a black dotted line, a black particle. So I will associate a field phi blue for the blue particle, a field phi red for the red particle, and the field psi for the black particle. And so we would write down a term which is called the interaction term, which tells you how the particles are interacting. So here, the red particle and blue particle are talking via the black particle. So you write down a term in the description, which is basically cubic in the fields, phi blue, phi red, and psi black. So there are 3 fields, so that is why they are cubic in the fields. So when we talk about Feynman diagram, so here on the left, a red particle comes in and a blue particle comes in, they interact, something is going on, and that interaction strength is parameterized by this coupling G. The red particle is labeled by its momenta. So in this particular case, there are 4 momenta. So mu takes on values, 4 values, time and 3 space. So typically we denote the time component by 0 and the space components by 1, 2, and 3. So this is the 4 momenta of the red particle, and similarly there's a 4 momenta of the blue particle. So they will have independent momenta P1 and P2. At the point of interaction, there is going to be momentum conservation, which essentially means that the momenta that the black particle is carrying is going to be the sum of the momenta of the incoming particle. So we have a momentum conservation of this kind. And then they again split back into the red particle and blue particle. So there is a probability amplitude associated with this kind of a process, and you can sort of guess on the grounds of symmetry what this probability is. So first of all, there are 2 G's corresponding to the fact that there are 2 vertices. So here when the particles interact, we call that a vertex. So the coupling constant G tells you how strong that interaction is. So in this diagram, there are 2 G's. So the probability amplitude is going to be proportional to G square. And then intuitively, you can actually reason that if the interaction so happened, this momenta was designed in a manner such that the relativistic invariant, which is simply k mu contracted with k mu. So instead of having the simple 3-vector dot product, we use the Lorentz dot product. So the Lorentz dot product is very similar to the 3-vector dot product, except that you have a wrong sign. The time component comes with the opposite sign compared to the rest of the 3 spatial components. So you want to construct something that is an invariant under that dot product. So the invariant is going to be k mu. And this we label by, it's a standard notation, we label by S. In whatever follows in my talk, I'm going to call this S1. But typically in physics literature, you will see this notation S. So that is why this kind of an exchange interaction where you see S appearing in the formula is called the S channel. So just get familiar with the notion of a channel. So a channel means that the probability amplitude in whatever I'm going to talk about is going to take on this form. So there is going to be a pole at m square, and m square is simply the mass of the particle, this heavy particle that is getting exchanged. So I will assume that this black particle is heavy and it has got mass capital M. But you could also write down another diagram. So the rules are that you fix the position of the red particle and blue particle. So don't alternate, or don't change the ordering of the red and blue. But keeping these ordering fixed, we can have another kind of diagram, which is where you actually interact in this manner. And so again, by momentum conservation at this vertex, P1 momentum comes in and P3 momentum goes out. So you will have the momentum conservation here is going to give you P1 minus P3. And there is a relativistic invariant made up of P1 minus P3, which I'm going to call T. And so you'll have another probability amplitude which is given in this manner where the kinematic variable, that appears is the relativistic invariant made out of P1 minus P3. And this is conventionally denoted by T, and this is called the T channel. So in this particular example, where we have two kinds of particles, red and blue, there are two channels. So there are two channels, S channel and T channel. If you have the same colored particles coming in and same colored particles going out, so if only red particles came in and red particles went out, there will be another channel, which will be the U channel, and that will introduce an extra term, which is absent when you have these colored particles. So in this particular example, the total amplitude is just the sum of these two amplitudes. This is a scattering amplitude. Remember that in quantum mechanics, we calculate the probability of a particular scattering event happening. And as you can make out that if I added the S channel and T channel, we are going to have an object that is invariant under ST symmetry. It is just simply the exchange of S and T. So this exchange under S and T is what is called crossing symmetry. So in this example, it's a simple interchange of S and T. The operative thing that you have to realize is that when we are calculating using quantum field theory, we are adding channels. We have, in this particular example, both channels present. Is that clear? Are there any questions? Okay. So this is what I wanted to emphasize, that we have both channels present. And so why should quantum field theory tell us that there should be a parameter in representation of the kind that you just now saw? So as I said, that when we are talking about physics that is happening at very low energies, the intuition could be that the very high energetic particles, very massive particles, may not be relevant for the description because you don't have enough energy to excite those particles. And so you could ask, are these heavy particles totally redundant in describing this physics? And the answer is no. In fact, if we had powerful accelerators where we could scatter particles at very high energies, we would be able to excite these particles. And so contrary to what the naive expectation could be, is that these heavy particles will leave their imprints on low energy physics. And let me give you a non-standard explanation for this, how to see that you will have an imprint from the heavy particles, in spite of the fact that you may not have enough energy to excite them. So when we compute experimentally measurable quantities like scattering amplitudes, then these quantities should not care about what we call the field, as long as the in and out states are untouched. And the reason is because, as I told you, what we are scattering, the particles are labeled by two numbers, the relativistic momenta, the 4 momenta, and the spin. So long as those are untouched, whatever the intermediate description we use should not affect the final quantities that we calculate. This is similar in spirit to trying to do an integral and doing a coordinate transformation to just put it in some more convenient form. So when I use the notion redefinition of fields, you can map it to what we do when we do a coordinate transformation when computing some difficult integral. So we should be allowed to redefine our fields, and the observable quantities should remain invariant. And this kind of a problem is usually set as an exercise in a first course in quantum field theory. And of course, I don't expect you to think of this as a theorem, because I've not proven it as a theorem, but I'll just ask you to believe me. So here is what happens. So let us now go back to this picture of the spectrum and say that we are having these kind of interactions where two light fields interact with a heavy field. So phi1 and phi2 were light fields, and psi2 was a heavy field. The quanta of excitations are the particles. And as I said that we are allowed to redefine our fields, so let's redefine the heavy field. So let's redefine the heavy field in the following manner. Psi2 goes to psi2 plus lambda times phi1, phi2. This is a consistent redefinition because the nature of the psi2 quanta does not change on doing this redefinition in quantum field theory. But if you just substitute this redefined psi2 inside this interaction here, phi1, phi2, psi2, you're going to get an extra piece, phi1, phi2, phi1, phi2. And this would look, in the diagrammatic sense, as if a red particle comes in, a blue particle comes in, and They all meet at a point, and a red particle goes out and a blue particle goes out. So this is to distinct between from the previous diagram where there was an exchange happening, this black dotted line that you saw. Here we have just a contact interaction, and the interaction is happening at a point. But now see what has happened. Phi 1, phi 2 are light fields, and because of this redefinition, we have now a new term in our description which only depends on the light fields. So here is the imprint of the heavy fields. And so this is the important lesson we learn. If we truncate the heavy fields, then the observables involving only light fields will know about the heavy guys through this ambiguity which we introduced. So lambda here is some arbitrary parameter that I introduced. So there is some ambiguity dependent on lambda. And this is precisely the physics origin of this parametric ambiguity in pi that I expect to be there in a physics representation for pi using quantum field theory. So is that clear? Are there any questions regarding this?
Yeah, so you're saying this lambda, that's more or less the lambda in the pi formula, is that right?
Yes, that's right.
Yeah. Okay, great.
So this means that if pi, for instance, has a quantum field theory way of looking at it, then the truncated series sum must have at least one parameter ambiguity in it. And the same goes if you think in terms of the Euler zeta functions. Summing over all modes, including these heavy modes, would make this dependence on this parameter go away. And this is exactly what happens in quantum field theory as well. If you actually keep everything that is there in your original description and you don't do any truncation, the final answer for the observables is not going to depend on this, field definition parameter that I introduced. Now you could think that can we make use of this ambiguity? And here also we have a notion in physics. So obviously if you have some quantity that you're observing, you know that it is not going to depend on this lambda. But suppose you're using this observable using some finite number of terms, you would expect that the partial derivative of that observable that you're measuring in experiments, the partial derivative with respect to this parameter should at least be approximately 0. If you did not do the truncation, you kept everything, then it is obviously not there. It's just a redundancy in the representation. But if you use a truncated representation, it will be there. And then the question would be that you want to use those values of lambda such that this observable, the partial derivative of this observable is at least approximately 0. And this picture here gives an illustration of what is going on. So for example, suppose you took pi and you worked with a truncated representation. So here I've truncated that series up to 20 terms. And here on the x-axis, I have plotted log of lambda. So in fact, it has a huge range of lambda here. As you can make out, it hugs the exact answer for a long time. And then as you expect, it has a different rate of convergence, because if you made lambda very, very large, then the terms in the series would become similar to the Madhava series, and the Madhava series has a very slow rate of convergence. So this is what happens. And so what you would be looking for, suppose I did not tell you that pi is 3.141, but I actually told you to calculate pi using this truncated series, you would try to find plateaus in the numerical approximation, and then the flattest plateau would give you the true range of pi, a true value of pi. So this has this kind of an equation also has a physics analog and goes by the name of renormalization group equations. So just to let you know that there are these analogies that we have so far as physics is concerned in trying to make use of these truncated series, truncated parametric representations. So with this as the background, we are now ready to discuss the puzzle in string theory. So this brings to the Euler beta function, which in string theory literature is called the Veneziano amplitude, after Gabriele Veneziano, who made this observation in the late 1960s. Then I'm going to explain the puzzle and what its resolution is. So the Euler beta function is just a ratio of gamma functions. In my notation, I'm going to use minus S1 and minus S2 because I want my poles in this formula to be at S1 equal to positive integers or 0 and S2 equal to positive integers or 0. As you all know, this has an integral representation. So this is how Euler started by, he was looking at this integral, how to do this integral. And the integral representation takes on this form. And immediately it should become clear that this integral form, suppose you wanted to put this on a computer and evaluate this numerically, you would require to specify some S1 whose real part of S1 and real part of S2 are less than 0. Otherwise, this integral would just be infinite. So the integral form requires an analytic continuation to make sense of in other regions of S1 and S2. So what you do next is you can binomially expand the 1 minus z piece, or more rigorously you can use a dispersion relation, which I'll talk about in a bit. And you reach the single channel pole expansion, which everybody is familiar with because you can find this in a table of integrals and products, where the beta function, this Euler beta function or the Veneziano amplitude, is represented as the sum over only the S1 poles or as the sum over S2 poles. And now, of course, it should become very obvious that this representation in terms of the poles in only one variable does not converge everywhere, because the original function has poles also when S2 is positive. So this must have some finite region of convergence, and this converges only when the real part of S2 is less than 0. And correspondingly, the other expansion, where you have poles only in the S2 variable, requires the real part of S1 to be less than 0. So this is what I refer to as a single channel expansion, or only one channel. So remember, just to remind you, in the quantum field theory example, we had both channels. But here, the Euler beta function, which is supposedly an analog of a valid amplitude, a scattering amplitude, has the way that I'm presenting it, has a single channel representation only. Now, here is where the puzzle in string theory comes out. So if you look at the older famous literature from the mid-1970s, so for example, this is a famous physics reports article by Stanley Mandelstam, one of the original contributors in quantum field theory, and after whom these Mandelstam variables, so the S and T that I was showing you in the quantum field theory, they are named after him. He talks about a distinction between what you would do in quantum field theory. This is what you mean by scattering elementary particles, where you are summing over both channels. So here is the T channel that I showed you, and here is the S channel that I showed you earlier in my talk. And here is what you would look at when you look at scattering in string theory. You would actually compute only one channel, and it would be equal to the expansion in the other channel. So this is what goes by the name of dual resonance models. In the modern literature, this goes by the name of worldsheet duality, just to make a distinction between the other forms of duality that string theory has. But this automatically raises a puzzle, and the puzzle is the following: that there is a lot of work in a version of string theory which is called string field theory, which is close in spirit to quantum field theory. And if it is close in spirit to quantum field theory, you would expect that it must have a representation where you're summing over both channels, not just one, and it should make all the analytic properties of the amplitude manifest. And this first line here, where I'm just summing over the two channels naively, this obviously is wrong, because just imagine that you try to do that by saying that, okay, the beta function must be maybe just the sum of this plus this, but obviously since they're equal, maybe I should try to put a half, and I would do half of this plus half of that. But immediately you realize what is wrong. If you try to calculate the residue at S1 equal to n, it would get an extra factor of half, which is obviously wrong. And the reason is, when you put a half of this and try to sum it with half of that, the resulting quantity does not converge when S1 is bigger than 0 or S2 is bigger than 0. It only converges when S1 and S2 are both less than 0. And if both S1 and S2 are less than 0, then that series representation does not have any information about where the poles are. So you can't do something like this in the first line naively. Rather, what is missing actually is this other contact term piece that I introduced when I was trying to explain the field definition ambiguity. So this is the piece that was actually missing in the formula. And if we found a suitable form for this contact term piece, then indeed such a representation which is consistent with what we expect from quantum field theory would be possible. Now, strangely, an explicit analytic formula for this quantum field theory expectations does not seem to exist in the physics or maths literature for the Euler beta function. And of course, as I said, one could have been anticipated using string field theory, but nothing was ever explicitly written down. Now, the story becomes a bit funny, because if you open Gradstein and Rizek, which is this big fat book on tables and integrals that any theoretical physicist has, there is another formula for the Euler beta function, which one can reach from this integral representation by doing a coordinate transformation. And if you do this Taylor expansion and term by term integration, you actually get a representation which has poles in both channels, and you address it with some polynomial in S1 plus S2. And you would have thought that, but hey, this looks like quantum field theory. So isn't this what you would identify as what would arise in a quantum field theory description? And the answer is no. This is still not what would arise in a quantum field theory description, because this still has a finite region of convergence, and this the convergence here requires the real part of S1 plus S2 to be bigger than -1. And in quantum field theory, you expect the non-analyticity only at the poles, the physical values of the masses that are getting exchanged in the interactions. So even this representation requires analytic continuation. It does not have this parameter that I expect from quantum field theory arguments, and hence is not in accordance with quantum field theory expectations. And very curiously, I did a lot of search, and it in the old string theory literature, it is only mentioned in one paper, as far as I know, in a 1971 paper by Nakanishi, and it's never mentioned anywhere else. So the resolution is this new series for Euler beta function that we introduced, that we found using this dispersion relation techniques, and this is what Halmar also found using the partial fraction technique. So you now have poles in both channels. You have this extra piece. You have this parameter here. The dressing factor is a polynomial in S1 and S2. And if you do an analysis of convergence, if you looked at the first term on its own and the second term on its own and the third term on its own, each of these pieces converge on their own. So you don't require to actually think that there must be some secret infinity that cancels off between each term. So this particular representation, which is for the Euler beta function, the Veneziano amplitude, requires here real part of lambda bigger than bigger than 0. The thing that we mentioned in our paper actually had a shift in the denominator. The gamma function in the denominator was gamma of 1 minus S1 minus S2, and that is what you get in open superstring theory, but you get a similar formula for the usual Euler beta function as well. So again, why did this formula not exist in the literature? Now, at least from my perspective, it did not exist because we used a local crossing symmetric dispersion relation. So this is a bunch of words which might be very heavy, but I'll explain to you what these mean in a bit. And this did not exist before our work. So, and as I said, there is a similar formula where you have a similar series representation for where the denominator has this one shift. And the formula for pi that I exhibited came from that series representation when I replaced S1 by -12 and S2 by -12. But as is evident, there is a family of such pi formulas coming from generalizations of this Euler beta function. Okay, so how did we arrive at this at these formulas? So I'm going to sketch this derivation using dispersion relations. So if I went through the algebra very carefully, it would be a 2-hour talk on its own. So I will just sketch the derivation, and if you want, I can give you more details later on. But in light of the fact that I'm already running out of time, let me just sketch in brief what the derivation was. So we require novel dispersion relations. So what are dispersion relations? Dispersion relations in physics, or in the way that I'm using in quantum field theory, are nothing but a fancy application of Cauchy's residue theorem. Now, if you just had a function of one variable, it would be very easy to write down these dispersion relations. So what you would do is you start off with Cauchy's formula. You start off with the contour that encircles a point, and that would give you the value of the function. Now let's imagine that the function is known to have some branch cut along the real axis. So what you would do from this Cauchy's formula is you would deform the contour, and you would wrap your contour around the branch cut, and also it would encircle the large arc at infinity. So you would get some contribution from the arc at infinity plus the jump across the branch cut, or the discontinuity of the function across the branch cut. So you'll get a formula of this kind. This is what we call a dispersion relation, because we can recreate the function anywhere in the complex plane just by knowing the discontinuity across the cut. So a set of poles, if you have poles along the real axis, would also be amenable to this kind of a dispersion relation, because the discontinuity across a pole is just a delta function. So if we could throw the arc at infinity, which essentially means that we need to have some fall-off condition for this function, then we would be able to know the full function by just knowing the discontinuity of the function in the complex plane. And this is the one variable version. The one variable version is very simple. The two variable version is more complicated and requires some cleverer tricks. So the first subtlety that one encounters when using these kind of ideas is what happens if the arc does not die. So for example, if the absolute value of f of z went to some power law like this, when z goes to infinity, then this has a simple cure. We, instead of actually starting off with this simple Cauchy's formula, we would start off by dividing the function by some power of z minus z naught. The penalty that we pay here is that we've introduced an extra subtraction constant. So in physics, this z naught, arbitrary z naught that we have introduced here is called a subtraction constant. So which essentially means that the value of the function at this subtraction constant will also enter the formula. And from a physicist's point of view, this is perfectly natural to expect, because this is very similar to what we do in renormalization. So in renormalization, when we remove infinities that we encounter in our answers, we actually need to supply some experimental inputs. The subtlety too with non-trivial resolution is if you have two variables, and this is what our formula for the Euler beta function is. The Euler beta function is a formula of two variables, and it is symmetric under S1, S2 interchange. And this is the amplitude of interest, which is crossing symmetric, permutation invariant under S1 and S2 interchange. So how do we write down a dispersion relation now? So conventionally, when we do quantum field theory using dispersion relations, what we do is, because of the fact that we don't have cleverer techniques, although mathematicians may have cleverer techniques, but as physicists, we just want to recycle the one variable intuition. So what we do is, we just hold one of the variables fixed. So for example, you can hold S2 fixed and treat the rest of the function as a function of only S1. So here it should be S1, not S1. And this is what is called a fixed S2 dispersion relation. But as you can make out, if you are holding S2 fixed, this would actually break crossing symmetry. And then your representation that you would get would not have the S1, S2 interchange invariance. So this is what we developed over the last several years. We were interested in this to understand these algebraic equations for calculating critical exponents, as I mentioned in the first part of my talk. So we came up with crossing symmetric dispersion relations, and these are also not new ideas. In fact, we sort of resurrected an old paper by Oberson and Khoury, which was written in 1972, and it seems to be a sort of in my research career, this has happened multiple times where we have found hidden gems in the literature. And by gems, I mean that this paper actually had only 7 or 8 citations when we discovered it. And this paper essentially had all the key ingredients, which I'm going to tell you about. So to build a dispersion relation where you have this S1, S2 interchange invariance manifest, you have to forego working with the Mandelstam variables or these S1, S2 variables, at least at the onset. You can, after you've done some clever things, you can reintroduce them. That is what we are going to do. But at least in the intermediate steps, you cannot work with S1 and S2. And this may be the reason why they were not really in favor so far as physicists were concerned, because they wanted to actually work with these standard kinematic invariants. So the logic is that we make a suitable change of variables from S1 and S2 to say Z and A. So Z and A are both complex variables. So S1 and S2, we are also thinking in terms of complex variables. And here A is a crossing symmetric function of S1 and S2. And so what we are going to do is, after we introduce these variables, this change of variables, change of coordinates from S1, S2 to Z and A, you could do anything that is creative to find a suitable A. We are going to hold A fixed and then write down a dispersion relation in Z. And that's the idea. So we're going to again recycle Cauchy's theorem once we do this change of variables. And for this two-channel case where you just have S1, S2 invariants, there is a simple natural choice for A, which is simply you take S1, S2 divided by S1 plus S2 and call that A. You can come up with, as I said, that you can be more creative. You can come up with other choices that will make it harder for you to parameterize S1 and S2. But if you make this choice, there is a very simple parameterization. So S1 and S2, the coordinate change is simply this. So this explicitly tells you how to go from S1, S2 to A and Z. So once you do this, you just go and write down a dispersion relation in the Z variable holding A fixed. And this is what Oberson and Courier essentially done for the three-channel case. The three-channel case is more complicated. A three-channel case has three variables, S1, S2, S3, subject to an extra constraint, S1 plus S2 plus S3 being held fixed. The two-channel case is simpler in some sense because we just have two variables, S1 and S2, with no constraints between them. So in this paper that I wrote with Prashant, we found a two-channel crossing symmetric dispersion relation, which takes on this form. So what does it look like? Let me just spell it out. So there is this subtraction constant that we have to introduce. So this is the penalty that we pay because we need to make sure that the arc at infinity dies. So if the arc at infinity does not die, we need to introduce this Z naught, if you remember what Z naught was in the Cauchy's theorem. And it is an integral. The integral starts from the first pole, pole or the location of the branch cut that this amplitude has. This curly A is nothing but the S1 discontinuity of this function M. And this is the cleverness. This second variable gets replaced by a ratio of A and this integral variable that we have. So this discontinuity in what we need is going to be replaced by a sum of delta functions shortly, and that is what will enable us to carry out this integration straightforwardly. So A, again, to remind you, it was just a ratio of S1, S2 divided by S1 plus S2. So the story does not end there. There is a final piece in the puzzle, a final subtlety. And the subtlety is that A is S1, S2 divided by S1 plus S2. And when we expand around A equal to 0, we will start getting negative powers of S1 plus S2. Simply say that A to the power n is going to have some S1 plus S2 to the power n in the denominator. And we do not expect such negative powers from a physics consideration, because from the physics point of view, what this would mean is that we would have massive particles which would mediate long-range interactions. And that is something that we don't expect in physics. So the photon, the fact that it has a long-range interaction is because it is massless. Massive particles are supposed to mediate only short-range interactions. So we have to somehow get rid of these negative powers that you see in S1 plus S2. And this gives rise to additional constraints. Now, you could have thought that, okay, from the physics point of view, you just subtract off these non-local terms and you would be done with it. But what happened remarkably last year is that there is a closed form expression in terms of an integral that subtracts off these non-local terms. And this was actually first found by Chao-Ming Song, who is a statistical physicist in Miami, and he is not really from our field. He was just reading our papers because he had good taste. And what this means is the outcome, the end result of his analysis is that, or a modification of his analysis, I mean, he did not do it for the 2-channel case, he did it for the 3-channel case, but it's easy enough to repeat his analysis for the 2-channel case, is that you get a formula where you replace the second variable in the absorptive part by this combination S1, S2 by sigma. So this is what I call the local crossing symmetric dispersion relation. And this technology did not exist till last year. And that is the reason I think these formulas did not exist either. So as I mentioned, that we are going to deal with poles because the Euler beta function has only poles, and the discontinuities of the poles are just delta functions. Here is a simple example to see that it is a delta function. You just work out the discontinuity x plus I epsilon minus f of x minus I epsilon. You will see that this is just in the small epsilon limit, it just becomes the Dirac delta function. And as a result of which, we can simply do this integral. So this is the final formula for the dispersion relation. Now, if you paid any attention, you remember that there was S1, S2 entering these Pochhammer symbols. And this is where S1, S2 played a role. This is why S1, S2 entered the formulas. And so a simple exercise is that you take the Euler beta function, you work out the absorptive part, you'll see that it is just a sum of delta functions very simply here. You just plug this back inside here and you'll get the formula with lambda equal to 0 in whatever I showed you so far for the Euler beta function. And here is the key observation where we bring in the parameter. This is a trick that we discovered, that using this new dispersion relation, we can find a quantum field theory type representation for the generalized Euler beta function. By generalized Euler beta function, I mean that I shift the numerator by alpha and the denominator by beta, and I just use the dispersion relation to write down a series. This is the series. And what happens is, to note, is that the left hand side is invariant under S1 going to S1 plus lambda, S2 going to S2 plus lambda, and alpha going to alpha plus lambda, and beta going to beta plus 2 lambda. The left hand side is invariant, but the right hand side isn't, and that is why you see this lambda coming in the series. So the right hand side of the dispersive representation is not left invariant under these shifts, and that is the result. That is the reason why you see lambda appearing at the level of the summand. So that is the trick that we invented to introduce this parameter in our representations that QFT arguments seem to dictate. And this is what gave rise to this formula. This is a sort of a unifying series, because the integral formulas that I showed you, where you have only a single channel expansion of the Euler beta function, or this other form where you have these 2 channels, but it did not converge everywhere, then you would get both these series by doing appropriate replacements for lambda. The physics picture here is like so. It seems to indicate that we should be able to have a quantum field theory description where we specify how these 2 light fields interact with some higher spin heavy fields, provided you add the appropriate set of these contact terms. So I think I'm going a little too fast, so I think I'll pause there and ask if there are any questions before I breeze through the other slides, because I have already run out of time, but I do have a few more interesting things to point out. So are there any questions regarding this? Okay, I don't see any questions. So this series also gives us new formulas for the zeta function. So in fact, in our paper, if you look at the appendix carefully, you'll find that we have a new representation for the generating function of zeta functions, again with this parametric ambiguity. And by just looking at the series term in this generating function, you'll get a parametric representation for any Euler zeta function. So for example, we presented this in the main text as a representation for zeta 2. And in the large lambda limit, you recover the familiar representation for the zeta function, or the zeta of 2. So where do we go next? And this is where I hope we can get some inputs from mathematicians. because where we went next is the following. So first of all, there is an unresolved question. So in all the physics arguments that relied on field definition, we did not specify how many parameters we can introduce on truncation. So in the example I gave, I just redefined one of the heavy fields, but there are an infinite number of heavy fields because this is an infinite series. So if I truncate, I would be throwing away an infinite number of heavy fields. So the question would be that if we redefine using an infinite number of heavy fields, in principle, we should have an infinite number of parameters. So where are these infinite number of parameters? Now this is easy to sort of imagine what is going on. So you could actually say that you take your formulas which have this parameter and you expand around some point lambda equal to lambda 0. Now, because the left-hand side is invariant under the choice of that you're making of lambda, all the Taylor expansion coefficients of this series would be 0. So you get zeros, an infinite number of them, because any number of derivatives, the Taylor expansion coefficient would be 0. And you could say that, okay, let's start off with the original series and we add these zeros that we get using extra parameters. And you'll get, in this manner, you'll be able to introduce an infinite number of parameters. But what use this would be is not clear to me. Maybe if you're clever enough, you would get faster convergence, but I'm not sure. But I do expect multi-parameter generalizations of the formulas we found, but I don't really know how to get nice looking formulas barring the one that I showed. And using this kind of intuition, we can actually enlarge the class of these kind of amplitude string-like models. What we used was linear programming and machine learning. But let me, so this was a recent paper that we put out this Monday. So this actually enlarges whatever we have done so far. But let me conclude by summarizing some interesting findings from the math side in this new paper. So we want to consider a general class of amplitudes which have the flavor that they are string amplitudes. And so let's imagine that we have these integer poles. So you can actually do an expansion of this amplitude. So let's subtract off the massless pole 1 over S1, S2, and then let's expand in terms of Gegenbauer polynomials. So this is a standard thing that we do in quantum field theory when we want to analyze quantum amplitudes. So this is what the form we get from the dispersion relation is. The unknowns here are these C and Ls, these coefficients here. Because you want to have the idea that you have the notion of probability, you want these C and Ls to be positive or 0. So they have some nice positivity property here automatically. But what you find quite nicely from this kind of an analysis is a negativity domain, which means that any amplitude which has this kind of a form, such that this CNLs are positive, they satisfy a sign definiteness in some very unique looking domains. So so for example, if lambda was 0, you get the domain where this quantity where I've subtracted off the massless contribution to be fully negative. And if you introduce lambda, you get an enlarged domain of negativity. So the full domain of negativity where this quantity here is expected to be negative is this. And how do we constrain these amplitudes? So as I said, the probability interpretation needs this definite sign property for these coefficients in the Gegenbauer polynomial expansion. And we also need that the amplitude is also lambda independent. So we have this whole infinite number of constraints through this lambda independence. So there are two additional conditions that we use in physics. We specify two low energy data. So this is a low energy data because we are expanding the amplitude close to S1 and S2 equal to 0. And then we minimize this m bar at 0, 0. So I don't have time to explain to you, but physically what we are doing is we are minimizing something called entanglement. So obviously you must have heard entanglement if you went to any of these quantum seminars. Now entanglement is a buzzword. And what we found is that if we specify the supersymmetric superstring low energy data, we recover the CNLs which are very close to the superstring theory. And we expect that in order to implement this, machine learning is going to help because we really want to impose some condition of lambda invariance in this form So we choose two arbitrary values of lambdas, and we want this ratio to be as close to 1 as possible. Now, numerically, of course, it's not possible to choose epsilon equal to 0 because we are truncating. But this condition here is a nonlinear condition, and it is difficult to use linear programming to frame this problem. And what we found is that machine learning techniques help. And so, for example, here is an output. If you compare the exact answer from the string theory side from what we get from the bootstrap or this way of constraining amplitudes that I described, this goes by the name of the bootstrap. Then these come very close to the actual answer that is known from string theory. So this actually says that the string amplitude seems to be some kind of an extremal function in this problem of the bootstrap. So if you look at the space of theories, you get a whole kinds of interesting space of theories. The black line corresponds to hypergeometric deformations of the string amplitude. So the explicit analytic formulas for these hypergeometric deformations can be found in our paper, and the original references which found these hypergeometric deformations as well. And the string is just one particular amplitude which satisfies all these constraints. So here are my conclusions. The product of these three gamma, so the form that we had gamma divided by gamma, but there is another interesting form that arises from string theory, which is there are three gamma functions in the numerator divided by three gamma functions in the denominator with three variables, S1, S2, and S3, subject to a constraint that S1 plus S2 plus S3 is fixed. And this also is similar in spirit, except that you will see complicated square roots appearing, but the square roots go away when actually you simplify the answers, but you will see square roots appearing. And this physically corresponds to graviton scattering in string theory. And this again, in our way of doing, setting up the problem to generalize the string amplitudes using the bootstrap appears to be an extremum found reason. His was actually, his formula pointed us in the right direction. In our original paper, we had recycled the two-channel symmetric answers to find parametric formulas, and the three-channel symmetric answers that we had presented for this closed string amplitude did not have this parameter in it, but we now have a dispersive way to have this parameter inbuilt. So as I mentioned, that there is an interesting analytic deformation of open superstring called hypergeometric deformation, which has similar series representations. So you can see it in the appendix of our recent paper for the relevant formulas and references. And there is an open problem. Deformations of a similar kind of this hypergeometric nature for the closed string are not known analytically. So our numerical approach will give us these deformations, but analytic formulas for this are not known. So this actually proves that there is a lot to learn from interactions between physicists and mathematicians. And I will leave you with a thought. I have always believed that we should not be that arrogant to think that we have invented all the mathematics to understand the universe. And I believe that maths and physics should go hand in hand, and more dialogues are necessary. The kind of dialogues that we are having through this platform, but also some more interactions where we meet with mathematicians over coffee and we can bullshit and ask questions freely. So that atmosphere is, in my opinion, lacking. So unfortunately, at least from my perspective, this does not seem to be happening much. And I hope that that changes in the near future. So I'll thank you, and thank you for your attention. So please ask me anything that confused you or anything that I went by too quickly.
Thank you, Aninda, for a wonderful talk. Are there any questions for the speaker? So I had one question. Perhaps in future there would be Q analogs of the formulas that you obtain. Perhaps Hjalmar also has worked on finding Q analogs of a lot of things. So we could expect Q analogs of these formulas for pi that
yeah, you mean replacing n by the Q numbers?
Right. Because the zeta functions have Q analogs.
Yes.
So
yeah, indeed, that is a very good research direction to pursue. In fact, there are these Q deformations of the string amplitudes, which go by the name of the Kuhn amplitudes that are known in the literature. So the way that I have set up the problem right now, we can't analyze that because I've already specified the location of the poles. So I have said that this is an integer space spectrum. But if you were to modify that and leave the location of the poles or the spectrum unspecified, then indeed you should be able to analyze more exotic amplitudes, which are the Q analogs.
Hmm. Right.
Yeah.
So I have a question. May I ask?
Yes.
Yeah, so Aninda, thanks for a really nice talk. I was wondering, have you looked at Ramanujan's formulas? He has some hypergeometric formulas in chapter 10 of his, chapter 10 and some other chapters of his volumes. It's in volume 2 of Burnt's books. So there he takes hypergeometric series and he takes log derivatives. And many times when you take log derivatives, you'll get 1 over something plus s and plus minus s, things like that, because they come from the log of the gamma function. So
I see.
so these kind of sums where you have things in the denominator, those come in the log when you take log derivatives. And he has a lot of formulas. And in fact, he got some pi formulas.
I see. I see. No, I have not had a chance to look at them, but thanks for pointing that out. So this is
I'll send you the
yeah, that'll be very nice. Yeah,
specific
thanks.
chapter 10 or whatever. All right.
Yeah, that'll be nice. Yeah.
Any other questions?
Sorry, just quickly, I just wanted to look at that two-dimensional picture you showed with that strange region with the hyperbola, and
Yeah, this one.
yeah,
Yeah.
just to look at it. Sorry.
Yeah.
So what is the so there's a hyperbola, probably
Yeah.
xy equals 1 or something, and there's unit
Yeah.
square, and then what's the
Yeah.
part? What's the equation of the part above? Is there a
Yeah, there is an equation. So for the left-hand guy, you will find the equation given in our paper. So
Okay, I'll
it's a union of various domains. Yeah.
yeah, and there are exactly these 4 domains or whatever.
Yeah. So the way that this domain actually comes about is to find where. So you want the argument of the Gegenbauer to be bigger than 1. So the left-hand side that I presented here has lambda equal to 0. So that's an easy exercise to do. So you want for any n, you want this to be bigger, this whole combination to be bigger than 1, and also this kernel that is sitting here, you also want that to be bigger than 1. So the joint restriction gives you that domain that I showed. Yeah.
And there are these 3 or 4 factors. That's why there may be these components. Okay. Thanks.
So previously, when you had those formulas for pi, those also had terms which were similar to those in the argument of the Gegenbauer polynomials, right?
That's right. So so here, of course, you could come up with a similar representation for pi where you have the Gegenbauers instead of what we have, the Pockhammers that we had.
Right.
That would be different series expansion. And each term in that series expansion would actually have this negativity property that I showed.
Right.
So that would be different in spirit. So
there would be these constants which we don't know what they are, right? CLN.
The CNLs, in fact, people have worked out. They have some complicated form in terms of hypergeometric functions. So there are known results for CNLs. So that would be a different series representation for pi as well. Yeah.
Oh, okay, nice. Okay. So if there are no further questions, let's thank Aninda again for a wonderful talk. Yeah.
Thank you.
Yeah, these are really nice formulas. Yeah.
Yeah, I really enjoyed the talk, I have to say. So it's things get much clearer when I listen to you then.
Yeah. Thanks, Almar.
yeah.
Yes. Yeah. I wish we had a way to, this is what I was informally referring to as a bullshitting session. I mean, this would actually help us in a lot of ways, and this is something that I frankly feel that it would enrich both communities.
We are all bullshitters. You can call us to ISC and we'll be very happy.
That's great.
Come there.
Yeah, absolutely.
Yeah, you should come and visit us. Yeah, for a few days. Absolutely. Run the next one of those seminars out of ISC, maybe one special episode.
Was that sorry? I didn't.
I said they should come here and run one of the episodes of this seminar out of IISc.
Oh yeah, that
Make
will
a
be nice.
mystery nice.
Yeah. Or we can try to convince our director and divisional chairman that we should have a conference, bullshitting in mathematics and physics.
A BIMP conference. Okay, maybe we should
Yeah.
check.
Yeah, so there is one physicist at Durham, Daniel Dorigoni, and his work and my work sort of has some intersections, but I'm not able to understand anything from the physics perspective. But we are along the same period, we are working on similar things. So, I mean, it would be good. And I try to read his papers, but I mean, while I get some sort of idea, but there's too much physics for me. So,
Yeah.
so yeah, it would be actually nice to see how, yeah, I mean, such a conference would really benefit both the communities.
Yeah. I've been trying to convince Apurva that we should have some.
Yeah, I know. It's just too busy. I'm right now traveling as well myself, actually. So,
Yeah.
but yeah, we should talk more. Probably next semester.
Yeah.
I keep saying next semester. Damn, let's try and actually make it next semester. Yeah. Thanks. It was a nice episode.
My questions would be really more from physics point of view, so I don't want to really ask in this forum, but just something which may be sort of at the interface. Since what you're looking for is motivated from string theory or string field theory, where there are infinite number of fields which you integrate over and truncate. So in principle, this kind of directions would take you to infinite number of ambiguous parameters.
That's right. Yes.
And when
Yeah.
is there some optimal in that? Why?
Yeah, so this is what
is the
I
reason?
mentioned, that I do expect multi-parameter representations of these formulas, but you might think that you might be able to improve convergence if you added them in a suitable way, but that is like knowing the answer beforehand. How do you know?
When the main point of string theory is that even though there are infinitely many of them, they sort of package nicely into one simple world sheet theory.
That's right. Yeah.
So just arbitrarily introducing new parameters is not probably the
right. Yeah.
way to go.
Yeah. I mean, at least from the dispersion point of view, we couldn't see how to introduce multiple parameters except via this thing, that once you actually have a representation which has this parameter, you can do a Taylor expansion around some arbitrary point where the series converges, and then you get a infinite number of zeros, and you add these zeros in using some coefficients. Now that would give you multiple parameters, but why those are useful, that I don't know. I mean, maybe you can have faster convergence or something. So one could investigate that. I don't know. I mean, Halmar, maybe you will be able to tell us if you see multiple parameters in the partial fraction method that you discovered.
Yeah, I mean, I tried, but I mean, for those amplitudes that you study in your paper, I couldn't really introduce any extra parameters. But I mean, I think in principle you could write down a lot of these things with like products of lots of gamma functions and lots of parameters. But I mean, I don't know which of those would be useful. I mean, either for mathematics or physics.
Right.
Okay, then I think I will call off the meeting. I think Gaurav is muted.
Yeah, I was just stopping the stream. So yeah, we can. Yeah, thanks a lot, Aninda.